We're going to take a look at this. We're going to use these three data values as our averages. So we're going to look at the mathematics behind these three. All right, so 2.38, 0.73, and 0.54. The first two are both in meters there, so we know. So let's take a look at the math that's involved. So first we'll look at projectile motion. Then we'll see what we get for a spring constant using energy methods. So to begin, what we want to do is to look at the x and the y directions like we've done in the past, where we determine some sort of a value using projectile motion. So in the x direction, jot down the x that you got as the average range. Jot down the x value that you got there. And I'm using 2.38 meters as my value. This again was the average of the groups. Then I'm using the time that was the average of 0.54. Whatever the time you had was, jot that down right there. 0.54. Now, that's not the same time as the time in the y direction. Look at the y direction and read what I put in parentheses. On the way down. Now you got to think back. Think back to when we did projectile motion problems. We talked about the problem as really having two halves of it. First half of the problem is the projectile on the way up. It gets to max height. It pauses vertically instantaneously, and then it starts to come back down on the way down. So we're going to have to look at the y direction a little bit differently. So let's first start with the x direction. In the x direction, if we recall, we know that there's no acceleration, because gravity, the thing that accelerates an object, only works vertically. Gravity pulls down, as we recall. So there's no horizontal acceleration as always. Ax always becomes 0. And we've always said this year that we're going to use only one equation in the x direction at all times. And this is the equation right here. Vx is equal to x over t. Now, when we have an angle that we're given, we're able to determine that angle and use it with cosine and sine. But we don't have to worry about that right now because we know what the actual x displacement is, and we know what the time is. So let's take our displacement of 2.38 meters, the x displacement, and divide it by the time period of 0.54 seconds. This will give me the velocity in the x direction, which I know is the same throughout the whole problem because there's no acceleration here. So for my number, I'm getting around 4.4 meters per second. Again, if you're using your own data right now, you're going to get a number that's a little bit different. That's fine. Okay, so if you want to challenge yourself, again, use your group's data and go along with it. Simple calculation, right? Divide x by t. Now, again, we need to make sure this is very clear. The value of Vx is a constant in all of these problems. Remember, gravity only affects the y velocity. Gravity makes the velocity increase on its way down to the ground, negatively. Whereas in the x direction, remember when an object is launched, okay, it's traveling with the same x velocity the entire time. It's what's happening is this. It's slowing down in the y direction, slowing down in the y direction. It pauses in the y direction, but it's still moving left, or in your case, right. And then it starts to move negatively and to the right. So the y velocity becomes negative now, but the x velocity is still 4.4 meters per second. The other reason I remember that this is never going to change is because acceleration is 0. Whenever acceleration is 0, your velocity must be constant. Definitely something for the midterm that you need to understand and know. Most of you remember that already, but whenever you have acceleration equal to 0, you got to be moving either with a constant velocity or really no velocity. But even if you have no velocity, it's still constant. It's constantly 0 in that case. Okay, so in this problem, the velocity in the x direction is 4.4 throughout the entire problem. When the catapult is launched all the way until it just hits the ground, the x velocity is always going to be 4.4. Now, the y direction is a whole other case or story. If you recall, the object is launched from here. It gets to max height, and then it continues its path on the way down and it hits the ground over here. On the way up, the velocity starts and then it decreases, it decreases, it decreases, until Vy becomes 0 at the top. Okay, Vy in the beginning has some velocity, it's some number. We don't know what it is, but there is some initial velocity, okay, here that is launched with. And then at the end, there's some Vfy. Okay, there's some Vfy at the end of this problem. But what we're looking at in the y direction is the velocity on the way down. So starting at the top of the parabola, falling down to the ground. If we're starting at the top, the velocity in the y direction at the top, again, is 0. So we can start by making that 0, which is already done for us right here. But what's the time going to be from the top to when it impacts the ground? Not the whole trip, but from the top to when it impacts the ground. What's the time in this case, Kat? It is half. Very good. So whatever your time was in the x direction, just halve it. For me, half of 54 is 27, so I'm going to put 0.27. Depending on your time in the x direction, just take half of whatever it was. Why is this true again? We assume the parabola is, what's the word? Symmetric. Okay? We assume it is symmetric. It's not always true, to be honest. Okay? On the way up and the way down, air resistance impacts a motion of a projectile differently, but we're assuming that there's no air resistance anyway, so we can say that these are symmetric. Now, it takes that much time for the object to hit the ground from the top of its path. We know the velocity at the top of the path is 0, because it does pause up there at the top for an instant. And then it starts to become negative, 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 negative velocity until it hits the bottom. Our goal is to find out the velocity on impact. Okay, Vfy. We know Viy is 0, so this bottom part here becomes 0 plus a times t. Okay, again, if you want to find out the final velocity, Vfy equals Viy plus at. Since Viy is 0, we don't have to worry about that portion of the formula. It goes to 0. So we get really negative 9.81 times 0.27, or whatever time you had for your groups. Giving me around, I'm going to give you one more decimal spot this time. Well, I'll actually round it. 2.6. We'll leave it at that. Negative, obviously, because it's a velocity going down. Now, again, your answer might be a little different from your group's data. The process is what's important right now. We'll get different numbers, and we'll talk about those numbers and how they're different or why they're different. So we've got the x velocity, and we've got the y velocity. But the y velocity is the velocity at impact, when it's about to strike the ground. Therefore, we could look at this next statement here and say the following. Since the horizontal velocity is constant and we have the final velocity in the y direction, we can say that we have the final overall velocity. And the way we do that is by using Pythagorean theorem. Think back. Pythagorean theorem tells us that a squared plus b squared is equal to c squared. Well, this is the velocity right here. In the x direction is to the right. The velocity in the y direction is acting down. So therefore, the overall velocity looks like this, which makes sense. Think about the parabola. When it impacts the ground, the velocity or the object is moving down and to the right. So that's why this VF is drawn down and to the right. Okay, again, it's moving this way in the x at the end. At the very end, it's moving this way in the x, and it's moving this way in the y, therefore giving you some sort of a downward right angle or trajectory of VF. So in order to find that, think about Vx as A, think about Vfy as B, and think about Vf as C. A, B, C of your triangle. Therefore, Vx squared plus Vfy squared equals the final velocity squared. So let's come up with a number for this when we solve for Vf. So you're going to square both of your velocities from the last part. Add them together and take the overall square root of that. So we've got the square root of 4.4 squared plus negative 2.6 squared. And remember, the negative 2.6 squared has got to be positive because you're squaring it. So you don't even really need the negative there. I'm getting 5.1 for mine. And think logically for a second. Go back. This is where you have to recall prior knowledge. If the overall velocity of impact is 5.11, then Vx and Vy have to be smaller than that. Remember, whenever you found Vx and Vy in our class, we did Vx was V cosine theta, Vy was V sine theta. It was always smaller than the actual velocity. So if we started a problem where the actual velocity was 10, we found out Vx and Vy, they couldn't ever be bigger than 10. They were always smaller than 10. Well, now look at what we've got. 5.1 is the overall velocity. And look at the two velocities we had in the components, 4.4 and 2.6, both of which are smaller than 5.1. Just to make a quick sanity check. So that tells us that the velocity of the wooden projectile on impact, when it hit the ground the first time, right, on impact, is 5.1 meters per second. What kind of energy does the projectile have the instant before it hits the ground? So it's launched, it's about to hit the ground. What kind of energy does it have the instant before it hits the ground? I definitely agree with kinetic. I don't agree with potential. Why wouldn't I agree with potential? Can somebody explain that part? It's definitely kinetic. You're right about that.
I thought because it's going down, it's like past the max height.
Not because it's past the max height. That's why I agree with kinetic. But I said, why is it not potential? It could have potential while it's moving. Remember, at the top, it's moving with potential. Why doesn't it have potential? Where is it physically located?
So the instance before this ground is basically at ground level.
Yeah, it's basically at ground level. Look at the parabola right here. It starts at ground level. It reaches max height. Then it gets back down to ground level. So the instant before it hits the ground, you could say that there's no potential energy there because its height is insignificant or it's negligible. It's just pretty much zero. So if we look at the next diagram down below, okay, take a look at the next diagram here. We're going to see how I identified all the types of energy for you. So, when you started this problem, the object or the catapult was pulled back, right? You pulled back on the catapult. Before you let go of the catapult, it had energy stored in the spring. It was a torsional spring. We'll talk about what that means in a little bit. But there was energy stored in the spring. It wasn't moving before you let go of it. It had no height. You pulled it all the way back before you let go of it. So it only had spring energy in the beginning. There was no regular potential and there was no kinetic in the beginning. Then it's launched. Along the way up, it loses energy due to air resistance. Q loss. It gets to the top. At the top now it has height and it's still moving at the top. Remember, when it's at the top, it's moving horizontally still. It pauses vertically so that it could go to the top and come back down. It's got to pause vertically. But horizontally, it is most definitely still moving. So at the top, because it has height and it's still moving, it's got both potential and kinetic energy at the top. It loses energy again on the way down. And then at the very end, right before it impacts the ground, it's got no height anymore, so there's no potential. It's not a spring anymore, so there's no potential spring. But it still is moving that instant before it hits the ground with this much velocity. So it has kinetic energy at the end. So what we're going to do is we're going to analyze these different instances of energy in order to eventually determine some characteristic of the spring. So we're going to work our way backwards. So we solved for final velocity a minute ago. So using that final velocity and the mass I gave you right here, here's the mass of the wooden projectile, 1.5 grams. Using this mass and this velocity, come up with the kinetic energy at the very end. At the very end. What's the formula for kinetic energy? Recall, what is the formula for kinetic energy? Kev?
Is it 1/2 mv²
It is. And since I'm looking for final, I'll put VF, just to specify. So I remember that I need to convert my mass, because it's in grams. I need to convert that by moving the decimal 3 spots. It's going to be a very small number. It's going to be a very small number, and you could probably figure out why that is. Why is it going to be a very small number? Why will it be a very small number looking at this? Use common sense. Why is our answer going to be small? Kat? Yeah, the mass of this thing is so small. And kinetic energy is a function of mass and velocity. Velocity is a relatively, not large number, but large enough. But the mass is quite small. So we have 1/2 times our mass of 0.0015. That's the mass of the projectile. It's the same for everybody. Now your velocity might differ. I got a number of 0.0195 joules. And keep 4 decimal spots here because these numbers are going to be very tiny here. I got 0.0195 joules as my amount of energy at the end of the problem. Again, if you're using your data, it might be a little different, but it should still be a rather small value. Okay, assuming, how many people are using their own data right now? Just give a heads up. What did you guys get? Just tell me real quick. What did you get for your VF in the previous part? I got 5.1. What did your group get?
6.37.
Okay, so yours is going to be a little bit bigger than this. Yours is going to be bigger than this also, a good amount bigger. 3.2 meters per second. So yours should be smaller than this number. Okay? Now, that tells us the amount of energy that this projectile has as it's about to hit the ground. As it's about to hit the ground. Now, consider and think for a second. Use conceptual understanding here. At the top, is it going to have more or less energy than the amount of energy it has at the end of the problem? Again, at the top of the path, is there going to be more or less energy than what you see right here at the end when it hits the ground? Give me reasoning too. Don't just give me an answer, but reasoning behind.
At the top, I guess it would have
Velocity is not zero at the top. Read, look. We have potential and kinetic energy at the top. So it can't have 0 joules. If it had 0 joules, the conservation of energy wouldn't hold true. Right? Kat? Stick with the first part you described.
Q loss.
Yeah, what is Q loss doing?
It's like decreasing the energy.
Exactly right. On the way down, the projectile loses energy because of the friction in the air. So at the top of the path, it's got to have more energy than it ends up with at the end because it lost energy on the way down. That's what Q loss means. So if we want to figure out the energy at the top, which we're going to do, PE plus KE, we'll do that in a minute, the answer we get should be bigger than the answer we just got for part 1 here. So let's go to the next page now to figure out PE plus KE. Now, how can I find PE? PE is mgy. That's where your Y max is going to come into play. So if I want PE plus KE, I'm doing this. mg times Y, which is really Y max, plus 1/2 m. Now, the kinetic energy at the top, if you recall, is from Vx only, because Vy at the top is 0. So this is really 1/2 m Vx squared. All right, so again, the PE from the top, you have to use mgy max. The KE at the top, you have to use 1/2 m, and we're using Vx squared, because Vy is 0 at the top, so we don't have to use that part. So when you plug in your numbers, go back to your first page to figure out these numbers, or your second page where you listed these values. Remember that with energy, 9.81 is positive. Please remember that. Only with projectile motion do we call it negative there. So again, your Y max might be different. I'll underline that in blue. Your work might be different right here. .73 is your Y max. If you go back up, look at your data. Your average Y max. Go back up to your data, all the way back up. Yeah, see the Y max you had? Okay. So again, the two things that are underlined in blue might be different for your group if you're using your own data, but everything else, the mass and gravity, and that all remains the same. So I'm going to go ahead and calculate what this number gets out to be. I got a value here of 0.0253. When you finish part 2, please read part 3. Try to make sense of what number 3 is asking you to do. It's saying compare the last two answers you got. If you have the energy at the top and the energy at the end of the problem, you subtract the two, you should get Q loss. So number 3 is telling you figure out what Q loss is by looking at the difference between your answers from numbers 1 and 2. If you look at that equation here, that's what this states. If you just subtract KEF, you get Q loss, right? So subtract KEF from the energy at the top. And if it helps you to do this, this is what I would be doing maybe in my notes. I would say this is the top, right? This is the end of the problem. So if you take the energy at the top minus the energy at the end of the problem, this is where you get Q loss from. The top energy minus the energy at the very end will give you Q loss. So take the sum of PE plus KE from number 2, and subtract KEF from number 1 on the previous page to give you Q loss. Let me take a look. So what we'll have is the energy at the top. Did anyone use the same data that I used? What did you get for the energy at the top? What was it?
The energy at the top was 0.0253.
253, sorry. And then the energy at the end?
0.0195 plus Q loss.
All right. So this is a 2 here. Let me correct this. This is a 2. So the energy that that wooden projectile has at the top of its path, the energy was this. The energy when it hits the ground was this. The difference in these energies is the energy loss due to air resistance. So that was our goal to figure out in number 3 here, was to figure out Q loss. So when I do 0.0253 minus 0.0195, okay, or whatever numbers you had, what do you end up getting? I left my calculator in the next room. What do you end up getting for this?
0.0058.
Yeah, that looks good. So what is this quantity? This quantity is the difference between the energy at the top and the energy at the end of the problem. And it loses energy on the way down. So therefore, this is really Q loss. Again, the energy that the projectile has at the top is some number. Say it's 7 joules. Then it hits the ground with only 5 joules. Where did the 2 joules go to? Q loss, that's the energy due to air resistance. That's what we're determining. It's just that they happen to be really small numbers here. Alright, so there's more energy at the top. It's got less energy at the end. If yours was backwards, it might have just been the fact that when you were measuring, you were estimating that Y max. That was the key that could have thrown this off. So if you get a negative number here, for the sake of now, or for the sake of today, just write yourself a little note. The number that you get when you subtract these should be positive. Okay, but I think there was one group that ended up with like a negative number. Don't worry about it too much for now. Now if I go back, I'm going to pause for a second and go back to the diagram. Well, actually, I'll just draw the diagram at the bottom. Okay, we're going to continue with this idea, but let's draw the diagram again. For those that weren't here yesterday, this might be a little bit of help also. At the beginning of the problem, there's potential energy stored in the spring because the catapult is pulled back. If you guys need to talk, just move together because you're in the same group. Just move near him. Just do it quietly. So this is the potential energy in the spring before it's launched. Then at the top, it's got potential energy and it's got kinetic energy because it's moving and it's got height. And then at the end, it's got kinetic energy here. Recall that on the way down, it loses energy. And on the way up, it loses energy. So that was our diagram. Now what we'll recognize here is this. This is an assumption that we're going to make. It's not necessarily true, but it's an assumption to make this a little bit simpler. The amount of energy that the projectile loses on the way down, we can assume is the same amount of energy it loses on the way up. Again, if it lost 0.0058 joules on the way down, we can also assume that it lost that much energy on the way up with this Q loss over here. These should be Q's, not O's. Q loss. All right, for those Q losses. So, as a result, here's what I could say. The energy in the beginning plus the energy it loses is equal to the energy at the top. Or rather, minus the energy that it loses. Sorry, minus the energy that it loses, because I'm reading the equation from here, if we solve this. Okay, the energy in the beginning of the problem, so you pull back on the catapult. Give me a number, an integer value. 10. You pull back on the catapult. It's got 10 joules of energy. You let go. The projectile does this, ready? It moves, it moves, it moves. Now maybe it only has 7 joules. Where did the 3 joules go from here to here? Air resistance. So if it was at 10 to start, and it got to 7 by the top, it lost 3 joules on the way up, it would lose another 3 joules on the way down, making the final answer 4. I'm using integers so it's easier numbers. So imagine you lose 3 joules of energy on the way up, you're going to lose 3 joules on the way down. So if we lost 0.0058 joules on the way down over here, that's the same amount we lose, so minus from the beginning, on the way up. So if you want to solve for the amount of energy in the beginning, if you want to get the amount of energy in the beginning, how do I get rid of that Q loss right here? Kat? Just add it over here. And that's what this says right here. Take a look. Read this. Spring energy, which is the beginning, is equal to the energy at the top plus Q loss. This equation that's circled right here is exactly the same thing as this. I'm just using words. So the beginning energy is this. That's the beginning. This is the top right here, and this is Q loss. So we have beginning is equal to top plus Q loss. That's exactly what's written below. Beginning, I can add the Q loss over, is equal to top plus Q loss. So take the energy you had at the top. In my case, it was 0.0253. The energy that you had at the top, that was number, I think, the answer you got in question 2. Yeah. The answer you got in question 2, the energy at the top. Add Q loss, which is the answer from question 3. Energy at the top plus Q loss, so 0.0253 plus 0.0058. Again, take the energy that you had at the top, add Q loss. Energy here plus Q loss will give you the overall energy you started the problem with. This is the energy at the top for me, for my numbers. This was my Q loss, so I'm going to add these two quantities together. 0.0253 plus 0.0058. again, beginning equals for me 0.0253 plus Q loss, which is 0.0058. That will give me the amount of energy that was stored in the spring in the beginning of this problem.
I have a question.
Yeah. You got it. Oh. Which means 0.0002. It's not 0, but it's a value. There is some Q loss. So just write in normal stuff. That's in scientific. Just write it in standard form. What do I get when I add those two numbers together? 0.0253 and 0.0058. 0.0311, and again I'm in joules still. Why is it, recall from yesterday, why is it a very small amount of energy? Because it's a small mass. It's a small mass. So this is the amount of energy that started off this entire problem, or whatever number you got for your group. Okay, the sum of the top energy plus Q loss gives me this energy right here. If I know that's how much energy I had in the beginning, I can use that to help me with the final thing we want to figure out, which is number 5. What's your formula for spring energy? What do you remember? Ignore what I wrote here for a second. What was your formula for spring energy, PES? Anybody remember the rest of the formula? 1/2 K. Yeah, in class we use this formula because we were looking at springs that stretch as a length. But did your spring stretch as a length in this lab? Or this experiment or whatever? It was called a torsional spring. You tightened it, remember? To put some torsion in that. So you turned it by an angle theta, really. You pulled back on the catapult. Here was the catapult. You pulled back all the way to here and then launched it. So how many degrees did you pull back, really? About 90 degrees. About 90. We're going to use this formula right here because it's a torsional spring. Okay, we're going to use, instead of that formula that I wrote just now, we're going to replace x with theta because it's a torsional spring. But there's something else you have to jot down, and this is not something that you need to know, honestly, for the rest of this class. It's just something that comes up. I don't want to give you the wrong answer. You're not going to use 90 for theta. What you're going to do, believe it or not, is what's called use radians. So we're going to use pi over 2 for theta. In math, and you haven't learned this yet, you'll learn it later this year in math class, there's a term called radians, which is just another unit of angle measurement. Just like centimeters and inches are 2 different units to measure length, degrees and radians are 2 different things. It turns out that 180 degrees is what's called pi radians. So if I want 90 degrees, it's just half of pi radians. This is not something that you know, and I'm not asking you to learn it. I'm just giving you the information. So if I want to figure out, I want to determine the rotational spring constant, that means solve for K. How do I solve this for K algebraically? Solve this for K. How would I get rid of the other variables and solve this for K algebraically? Steph? Divide by 1/2 or multiply by 2. Same thing, very good. And then divide by, what was it? Theta squared. Okay, I'm going to multiply by 2. Same difference, obviously. So what I have to do is I have to take 2 times the potential energy in the spring, which is my answer from the last problem. Take your answer from the last problem, plug it in for the potential energy in the spring, and take pi over 2 and plug that in for theta. So if I wanted to figure out the K value of my catapult, or the data I used, everybody's is going to be different because it depends on how much you twisted it, right? That was the K value. It affected how much you twist. So if I want to get the K value, I would use it for my data, 2 times 0.0311 over the quantity pi over 2 squared. Make sure you put your denominator in parentheses and square it, and then divide it into the numerator. And don't put any units down just yet. I'll explain the units in a second. Jen, what do you got for numbers for this?
Oh, those calculations because I wasn't sure if I had the algebra.
Anybody got the number for this one? Again, it'd have to be using this data, obviously, if you were calculating. It should be a very small number. These were not strong springs, obviously. 0. Seems about reasonable. Can somebody check or just see? Now, before I put any units on here, let's talk. What were the units of K? Stop. What were the units of K in the past? What were the units of K in the past for linear springs? Anybody remember? What were the units? What are the units for K in the past? It's not going to be the same as what we get here, and I'll explain why. But what were the units for K? Close. Not joules over meters, but that's close. Newtons over meters. Remember K meant how many newtons it takes to stretch a given meter? But are we stretching things by meters now? We're stretching it by an angle, aren't we? So as a result, what we can say is this. The units are newtons per, instead of degree, we looked at radians a minute ago. So it's in newtons per radian. So it takes 0.025 newtons to push this 1 radian. Okay, 1 radian. And 1 radian is a little less than 90 degrees. So in order for you to push this spring back, like this far, a little less than 90, it took you about 0.025 newtons of force. Is that reasonable? Think about it. When you were in the gym, did it take you a lot to pull back on that catapult? It took pretty much negligible force, like almost nothing. That's why this number is so small. The spring constant should be very low because you were looking at a torsional spring that had very little pushback to it. Which is also why the projectiles did not go as far as like across the whole gym. But there was one group, Mike, was it your group, that over-tightened it eventually. He was like, oh, if I keep tightening it, it goes further and further, which is true. But if you keep tightening it, it also pulled the wood columns together and eventually it snapped. So there was like a limit, there was a constraint to which you could tighten it. If you tightened it too much, it broke and it didn't work anymore. If you tightened it too little, it didn't actually launch well enough. So you have to find that in between. But that's why this number is so small, because it takes so little force to pull back 1 radian, which is less than 90 degrees. Yeah. Okay, what I want you to do with this is submit it to Dropbox, please. Okay? You do it right now. If you missed the first day of this, it's not a big deal. I recorded all the stuff we did yesterday, so I'd like you to go back, go through the process again, and then submit it to Dropbox, all right?